life, and I think I've got all the gadgets hooked up correctly. You can see the screen. Yes, okay, wonderful. So let's kind of just briefly recap what we were doing with the numeric integration stuff was right. You had an integral. You wanted to be able to approximate it numerically if it weren't possible or weren't practical to actually do it with the fundamental theorem of calculus. Okay, so um, so let's sorry, let me just open this my notes here. Um, yeah, okay, so let's take the, and let me go to, let's see, this, and I want MAT112. So let's sort of think about what is it that we did with, say, the rectangle rules, okay? Like, how did they work? What were we fundamentally doing? Yeah, go ahead. Well, don't jump all up at once here. Come on. Yes, you drew rectangles and then you, wow, right? Rocket science, huh? Okay, but what made this, like, what made your answer more precise when you, if you wanted to make it more precise? More rectangles, or an equivalent way of saying that would be make them narrower. Okay, so if you make the slices narrow, and then sort of add all that up, then you can make your approximation however precise that you want. Okay, and fundamentally, then, how was the integral defined? What did we do? So, like, if you go back to Calc 1, right, how was the integral formally defined? Okay, let me rephrase the question, or maybe better put, ask a slightly different question that will hopefully hint at where we're going. How was the derivative defined back in calculus? I mean, you don't have to say the formula, but just sort of what was the derivative? Right, okay. And but formally how it was defined was this, right? You had so if you have some function, oh, and I'm sorry, I need to put the, oops, damn it. I hit the wrong button. Uh Here. Right? What does that fraction define? It defines if I've got some curve and I have 2 points on it, this point is, say, at x and this one is at x plus h, then the slope of that blue line is defined by that fraction, right? Rise over run. Okay. Is that the derivative? No. How do I make it the derivative? Bingo. We take a limit, right? And then we say, okay, this is what defines the concept of the derivative, is by taking an approximate concept, namely that of the slope between 2 points, and then taking the limit as those points get closer and closer together. We did the same thing with the integral, right? If we take the idea of the rectangle rule, or either of the three of them, right, that we've discussed, well, what are those doing? They're approximating the area under a curve. And all we did was we drew a bunch of rectangles and added up their area. If we took the limit as the width of those went to 0, or equivalently as the number of them went to infinity, then what do we get? We get the actual integral. Okay. And then how do we compute these things? So how do we compute integrals? Well, there's two categories of approaches. One would be to use the fundamental theorem, right? And that's a really handy way to do it. But as we saw last time and the time before, it doesn't always work, right? Sometimes you have an integral that you just can't do with the fundamental theorem, like e to the minus x squared or something. And then what's the only thing you can do is approximate it numerically, okay? But fundamentally then, what is calculus up to? What do we do in calculus? You get close, and then you take a limit, right? And the limit part is what makes calculus calculus and not algebra, okay? Or something, right? Because what is it like? You talked about, think back to algebra and whenever you took it. You talked about average, or uh, what's the average speed? If it takes you an hour to get someplace and it's 60 miles away, what do you say? You'd say your average speed was 60 miles an hour, okay? But does that mean that your speedometer read 60 miles an hour every instant along that journey? Probably not, right? I mean, maybe if you had cruise control on, but it's only an average, right? Calculus is what's is concerned with the instantaneous, or in the integral sense, right? Geometry allows you to find the area of rectangles or other things that are bounded by straight lines by dividing them up. Calculus allows you to find the area of curvy things, okay, by taking slices, letting the number of slices go to infinity, okay? Okay, so what fundamentally then are we going to do? So let me graph. Okay, let me actually just sketch something. Okay, so if I had two functions, say we'll call this one f of x, and we'll call that one g of x, and let's pick two specific x values. Okay, how would I find the area between those two things? Okay, so let me just sort of sketch what area I'm talking about. Okay, so that's shaded area. Yeah. Right. We do some sort of integral. Okay. Let me erase for the sake of the what I'm about to do um, here. Okay. But what would I do to approximate the area? Well, could I draw a little slice between those two curves? Yeah. And I could figure out what the area of that slice is. Okay. So the area of the slice would be some sort of width times, let me call the particular x coordinate here x star, um, just meaning the particular one that I picked. Okay, the area of that slice would be what? Well, it has some width. Okay, let's call that delta x, as we've done before. And it has some height. What's the height of the slice? Well, it's whatever the top function's value is minus the bottom function's value. Make sense? Okay, so if that defines one slice, and if I were to do this on a whole bunch of other slices and then add them all up, that would give me an approximate answer, correct? Well, then what happens if I let delta x go to 0? Which is equivalent to saying take the number of slices and let it go off to infinity. Would that give me the exact answer? if I did that limit? Sure, right? Okay, so that's the area of one slice, and the exact value would be to do this. Right? The integral of the difference of the two things. Okay, but fundamentally, we'd be slicing this thing up. Okay, now I say the slicing business, so let me go back up to my picture here. Is that the only way I could have done this? What would be another way? Okay, fair point, right? I could have used trapezoids or some other kind of shape, but maybe a bit more fundamental than that, because all of those rules are very horizontal, right? In the sense that we are slicing things up in vertical slices, right? Whether those slices are rectangles or trapezoids or whatever is, but we talk about the width of all of them, and then we let the function determine the height. Now, why do we tend to do it that way? Well, because the functions, you give me an x coordinate, they return a y coordinate. But did I have to take here, did I have to slice this thing with vertical slices? Of course not. I could have done horizontal slices, or if I wanted to really be evil, diagonal slices. That'd be tricky, right? You could, right? But it would be tricky. Okay. So, point being, I could slice this thing up in lots of other ways. Now, for the particular example that I'm considering here, the vertical slices are probably the most convenient. Okay, just because of the nature of the coordinate system we use and how I drew my picture. But that doesn't mean that in every situation doing it vertically is the way to go, right? Okay, so maybe another example of this would be, let's take a shape where we could kind of do it either way. You know, if I, for example, drew a semicircle, and let me copy and paste. Okay, so let me draw two versions or two copies of the same semicircle. Right, if I wanted to find the area underneath that thing, what I could do is, oops, that's not the right button. I could slice it up this way and find the area enclosed by each slice, right? But I could also do it this way, right? Um, which way's better? Well, okay, there's that, right? Um, I mean, what is the equation for the top half of a semicircle, right? If I write it like that, or whatever, let's say it's radius 1, just for convenience, huh? Uh, well, okay, let me rephrase. That's the equation of a circle, right? What makes it just the top half or the bottom half is I say the y coordinate's got to be positive or not, right? Um, but if I wanted to think of it the vertical slice way, how am I going to rewrite the equation? I'm going to write it as this, right? And then what makes it the top half is that I took the positive version of the square root rather than the negative version. Okay, so plus square root would be the top half, minus square root would be the bottom half. Yeah? Okay, so the plus or minus thing. But if I did the other one, with the red slices, how would I want to think about it? I'd want to think about it that way. Okay, why do I have plus or minus here where I didn't on the blue version? Not just because I'm evil or tired. Well, yeah, exactly. So for the semicircle, we had only positive y values, well, or zero. But for the x values, um, uh, it's positive or negative. It's just that we never have negative y values in the particular picture that I drew. Okay, but I could have sliced this thing up either way, right? Are there any other ways that I could slice it up? Yeah, well, okay, good, good point, right? There are an infinite number of ways that I could do this. Um, Let me maybe actually, you guys mind if I move over to another sheet here? Is that okay? What's maybe one other smart way to slice this thing up? Okay, elaborate. Yeah. So Cole just said triangle, and I said elaborate. And then he said, well, is that right or wrong? I don't want to elaborate if it's wrong. It's the elaboration that's actually going to allow me to determine if it's right or wrong. Okay. So something like this, right? And then you could approximate the area left over by like doing that or something. Okay. Well, the geometry, the formulas would probably be a little nasty. Okay, but one theoretically could do that, and actually, this sort of triangle approach is how Archimedes did the parabola. Or, well, okay, I should rephrase. It's one of the ways that Archimedes did the parabola. He had actually gives two different approaches. Yeah. Well, uh, he okay, that's a complicated question. So the question was, without a computer, how did Archimedes sort of zoom in to see? Um, do you really need to zoom in though? Right? If you can, yeah, personally you do, but you're not Archimedes. No, all right. So no, maybe the better way to say that is that you don't need to be able to graph something in necessarily and zoom in on the graph in order to sort of come up with the idea of taking really narrow slices and then adding them all up. And that's, huh? Um, yeah, but of course the idea of equation, right, is itself somewhat modern. Um, yeah, this is how to put this. So one could argue that Archimedes, and he's not the only one that did stuff like this, that he anticipated what we call calculus, okay, by adding things up and sort of thinking about them as being tiny slices. Now, he thought about it in kind of a physics context also, which was um, if I take, let me draw a picture here. If I take a beam and I suspend from it two masses, and they're, say, at distances from this middle point, D1 and D2, under what circumstances does the balance? Huh? Right? If they're two unequal weights and possibly also two unequal distances, then under what circumstance does the balance, well, balance? You guys happen to know from physics? No? That's one way to say it. Here's another way to say it. Is that the ratio of the distances is inverse to the ratio of the masses. Okay. Now, In practice, how many of us use balances that don't have the balance point in the center? Okay, if you think about your playground in kindergarten, or think back to elementary school. What was on your playground in elementary school? A seesaw, right? Or teeter totter. No, you didn't have one of those. No, so small that it didn't have a teeter totter. Mm-hmm. Was it literally just you? Because the minimum number of children to need a teeter totter is two. Yeah, okay. But so I mean, just to wax poetic, I guess, for a moment. So when I was a kid in elementary school, I mean, yeah, we had a teeter totter, but one of the things that we noticed, or at least I noticed, was so you put one kid on one end of the teeter totter, right? And if I got on the other end of the teeter totter and we were about the same size, what would happen? Huh? Yeah, we would balance. Okay. But what about if I got like closer to the center point? I would go up and the person at the other end would go down. But what about if I got two people and we got part closer to the center point and there was one person at the other end? Yeah, we could balance out if we found the right spot, right? Well, what basically that meant we had discovered was this, right? Is that if you put, a fifth grader at one end and a first grader at the other end, what's going to happen? Boom, right? But if you put the first grader at the far end and the fifth grader kind of like along the bar somewhere, you can't find a spot where they'll balance, right? That's the law of the lever. Okay, so what Archimedes did was with the parabola is he imagined slicing it up and then putting those slices on sort of an imaginary balance and saying, okay, this slice would balance this thing, that slice would balance that thing, and if I can argue that every slice balances with another thing, then I can figure out, okay, what sort of is the balance point and the distances. And so what he basically determined for the parabola was that it almost like this: you take a parabolic piece, and then you take a triangle of appropriately constructed. And what he found was that the ratio at which they balanced the distances were 3 to 4, and therefore, what does it mean about the masses or the areas? 4 to 3, right? Because it's an inverse, right? Brilliant. Yeah, I feel like I should just make you guys read Archimedes over the weekend. Oh, okay, yeah. It's actually really hard stuff. That wouldn't really work very well. Yeah, okay. So, right. So we could slice this thing up in any number of ways. Okay. So that sorry, that was not the answer I was thinking that you would specify, but it's a perfectly good answer. What's another way I could have done it? I could have done pizza slice style, right? I mean, how many pizzas do you get that are sliced vertically? None, right? Huh? Well, okay, but they only ever do it with its thin crust, right? Uh, or you get cheese sticks, right, which are sliced vertically or horizontally, depending on which way you orient the box, right? Okay, so yeah, but you could also slice this thing in sort of pizza style slices and figure out what's the area of a pizza slice, uh, sort of imagining that the end of it is a straight line rather than a curvy thing. Um, are those exactly the same, right? So if I have a straight cut on the end versus the round cut like a pizza would be? Are those the same? Huh? Yeah, okay. Is the curvy black part right on top of the straight red part? No, of course not. Okay, right? But what would happen if I made my pizza slice really, really, really thin? It'd be closer. Okay. And so what happens if I therefore cut my pizza into an infinite number of pizza slices? It'd be infinitely close, and therefore they'd be equal, right? So I can slice this thing vertically. I can slice this thing horizontally. I could slice this thing radially. I could slice this thing sort of with those weird triangles that you would never actually do if it were a real pizza. Okay, yeah, I mean, you could, right? It'd look weird. Well, but where does that equation come from? Precisely, right? Um, yeah, so yeah, we didn't just, it's not as if Moses came down from the mountain and had two tablets with commandments and a third tablet that had sort of basic mathematics on it, right? It didn't happen that way. uh, so, yeah, I mean, it's too bad it didn't happen that way, right? And the area of the circle is, uh, alas, right? There were bigger problems than mathematics at the time, like, you know, don't be a jerk to your parents and quit worshiping that stupid golden bull or whatever it was, right? Uh, yeah. So, yeah. So where does the area of the circle formula come from? Well, fundamentally, it's because we can do this sort of thing, right? So, so the point here, right, is that I could slice this thing up in all kinds of ways, uh, but which way I choose to slice it requires me to do, you know, some sort of. It's going to change the equations or the formulas or whatever that I use, right? Because if I slice it up this way, we have to work in polar coordinates, which we'll actually talk about later in the semester. And you guys probably did polar coordinates like in your trig class at some point in high school or middle school or whatever. Did you learn polar coordinates where you specify the angle and the radius? Yeah. Okay. Um, right. So we'd have to come up with a different coordinate system to represent this, but we could do it. Um, and any of these methods are perfectly good, right? Uh, but in certain instances, it might be more convenient to pick one method of slicing than another method of slicing. For the semicircle, um, this is probably not a very convenient method of slicing it up. I mean, it would work, but probably not the way we want to go. Okay. Even though, actually, like I said, that's actually exactly how Archimedes did the parabola. So it's not an outrageous right approach, uh, except that like how many pizzas do you slice up this way? That would be really weird, right? Somebody's going to get a really a big old piece, and everybody else is getting the shaft. Okay, um, and you could slice it up this one of those two ways, and that's honestly probably how cheese sticks are usually done, right? Or you could slice it up like a normal pizza, like that, right? Now I really want some pizza. What do you guys think?
Let's order one.
Yeah,
Let's go to Arnie's right now. We can probably walk there before class ends.
we probably could. I doubt they're open yet. They're probably.
Make our own pizza.
So actually, I will tell you guys a funny story. So this is my very, I think my first or maybe second year. So I was teaching here at Wabash. So this is like 8 or 9 years ago. I was teaching Calc 2, in this room, and the class met at like, it was the spring semester, it met at 10 in the morning. And actually back then we started classes at 10:20. So there was this weird 20-minute gap or 30-minute gap. You had 8 o'clock, 9 o'clock, and 10:20. So there was this weird gap, and we eventually got rid of it because it was kind of silly. But and the reason that there was that gap in the first place is because it used to be in the Stone Ages that there was chapel every day, and so that little break was for when there was chapel. And that was also back when chapel was sort of a more religious thing rather than just basically a lecture of some sort. Anyway, so it so happened that I was teaching the class, and it was Mardi Gras, right? And somebody had a big cake on Fat Tuesday, and then they had leftover cake, and so they put the cake in the lounge next door, right? And then sent an all campus email that said, "Hey, there's leftover king cake in the Goodrich lounge." Well, I just happened to glance at my phone and saw cake in the lounge, and I was like, "All right, let's pause class." And so we took a break from class and went over and had cake. Yeah, it was pretty awesome, I have to say. Um, So I don't know. I mean, if we were in the afternoon, I'd call and order a pizza right now and just be like, need you to bring it in during class because we're talking about slicing pizzas. But yeah, anyway. Um, and those of you guys who are at home don't get any pizza, unfortunately, right? So you're SOL. Um, okay, so yeah, but you're going to choose the method of slicing based on what seems convenient at for whatever you're slicing up, right? So if, for example, let me just sketch something. Let's suppose that I was trying to find this area. What would be probably the way that I would want to slice it? I'd probably slice this one vertically, okay? Um, but that doesn't mean that I have to slice it vertically. It's just probably the most convenient. Um, Or if I had like, well, let's see, what would be a shape where I'd maybe want to do it horizontally? Let's do, um, here, let me go over to new sheet and draw something that's not ridiculous looking. Okay, so like, let's say, for example, that this is, here's the origin and, well, actually, let me do, actually, you know what, let me change the, let's do, this. Okay. So let's say that this point is -1 comma 0 and this point is 1 comma 2. Okay, so I'll just take x cubed and then shift it up a unit. Okay. Um, and then just for sake of for example, I'll pick the x values between -1 and 1. Okay. So in this case, could we slice it vertically? Sure. Could we slice it horizontally? Also. With and both would be sort of convenient. Now, in this case, which one is probably more convenient? I would say that the vertical one is because I've already got a formula y equals, right? And so that sort of inherently makes me think to do this vertically. So I would probably set this up like so, right? As an integral. But it's certainly not the only way that I could do it. How would I set this up if I wanted to work and think horizontally? Okay, well, what's the first thing I need to do? yeah, I need to find the inverse of the function, right? So I need to take y equals x cubed plus 1 and solve for x, okay? And if I did that, what would I get? I'd get the cube root of y minus 1, okay? Do we accept that? Yeah, just take this, turn it into that. That's pretty easy, right? Yes? Okay, but then how would I set up the integral? Well, what if I'm going to set up an integral, it's going to have to be something dy. Because if I slice it horizontally, then the thicknesses are what? Yeah, so the thickness of the slice would be running vertically. And, well, what should I call that? How about dy? Right? Okay. And so our integral that I'm going to form is going to be something dy. Well, I need to figure out three things, I guess. I need to figure out what's the thing I'm integrating and what numbers go at the top and the bottom of the integral. Okay. So what's the thing that I'm integrating? Huh? Okay. Cube root of y minus 1. This thing, the equation that I got here? Yes? Okay. Um, and sorry, let me think for a second. Yes and no. Um, if I were to integrate, so what would you think that I should write? This? Huh? Or I'm sorry, not negative 1 to 1, 0 to 2. Is that what you think I should write down? Huh? Well, okay, yes. Sorry, that's not what I meant. Is this though going to describe the area? Forget how we actually compute the integral, but is that integral going to represent what I'm after here? I claim no. Why? What is this integral going to represent? That integral is going to represent that and that. And in fact, what is the area of those two things? Yeah, they happen to be equivalent, like equal to each other because of the symmetry here, but uh, not the bottom left, but yeah, yeah. So I mean, those two areas are equal. But I'm not saying that one of them counts negative than the other, right? They're equal only because of the symmetry. Um, yeah, okay. Well, okay. Uh, but we could split it up and sort of think about it as two pieces because there certainly is the left-hand blue part where we do want to include that. But what about all this white stuff that's in there? It's not what I want. Okay. Well, I not so much change the bounds, but change the thing that I'm integrating. Okay, so let's go back to first principles and really think about how did I slice this thing up. Let me draw it actually in red so it's easier to see. What is my slice? Well, what's the height of the slice? Some tiny bit, right? And that's the thing that's going to become dy in my integral. But what's the width of the slice? Is it just the equation? Or sorry, the cube root of y minus 1? yeah, what's the width of that slice? Well, okay, that's for a subinterval, but yeah, it'd be whatever the right-hand thing is minus the left-hand thing. But what is the equation for this right-hand edge? It's at x equals 1, right? Just because of the particular picture I drew. So the integral that I would actually want to set up is this. Okay, the dy is the thickness of the slice, and that's a little vertical piece. Okay, so why is it 1 minus the cube root and not just the cube root? So let's think about that. Uh, it is that the thing on the left computes the blue shaded area, which is not what I wanted. Okay, so it is the answer to the wrong question, right? The area that I'm interested in was well, before I started shading and subdividing it, right? It was everything that was sort of between the curve and the line x equals 1 and the line y equals 0. So it's sort of like a um, this shape, right? Like a little chair or something. It was that entire area that I was interested in. Okay, is that okay? Yeah, Bueller, Bueller. You're supposed to say Bueller's not here today. Have you, none of you guys seen Ferris Bueller's Day Off? Yeah, okay. Yeah. Well, you know who did the worst baseball throw on earth? Hmm. Yeah, Dr. Fauci. Yeah. Well, there's a reason that he's a virologist and medical professional and not a baseball player. Well, that too. Yeah. So, um, yeah. Anyway. Okay. So why is it 1 minus the cube root is actually the width of the slice? How did I know that it should be that? Well, what is the equation of this vertical line at the far right edge of my figure? X equals 1, right? Good. All right, what is the x coordinate along the curve? Well, it's given by the cube root of y minus 1. Okay, and what do I want? I want the distance between those. And so, like when I do this vertically, if I do it vertically, what do? I do the top thing minus the bottom thing, right? If since I'm excuse me, working horizontally here, what do I do instead? Huh? I do the right thing minus the left thing. Okay, it's kind of the same as top minus bottom, but you just turn your head 90 degrees, right? To the right. If you turn your head 90 degrees to the left, then yeah, that's just not done. That's kind of like putting the cheese on the bottom of the patty. So yeah. Okay, so that joke didn't make sense to any of you guys, but it did to Cole because he's in computer science with me that meets right before this. So today in computer science we were talking about unicode, which is how you or a way to encode large numbers of symbols. So if you want to encode Chinese text, right? What's the problem with Chinese? How many symbols are there in Chinese? How many characters are there in Mandarin? It's a lot, okay, but when you say a lot, it's like thousands, right? Okay, Korean at least you use essentially an alphabet, right, in Hangul, right? But if you want to type things in Chinese, there are thousands of different symbols. So how do you represent that on a computer? Well, the way is you use an encoding scheme called Unicode, and Unicode also includes all the emoji that you guys use on your cell phones. So we pulled up some random emoji, and one of them was the hamburger emoji, where it's or cheeseburger rather, and it was bun, then cheese, then meat patty, then tomato, then lettuce, then the top bun. And this is just ridiculous. Yeah, but they had the lettuce and the tomato in the wrong order. It should be lettuce first, then the tomato. Like, I don't know what's wrong with you people, but um, yeah, we do. Okay, yeah. But all right. So sorry to digress about hamburgers, right? That um, right. So we can slice this thing up in a couple of different ways. And the area that we were interested in, we could either write as this or as that. Both of them, if we set things up right and we compute everything correctly, will give us the same answer. They ought to, right? They're talking about the same area. Okay, so if they don't give us the same answer, then what has happened? Either we've screwed up the computation or we've set it up wrong. Those are the only two options. Okay, and I'm pretty sure we set it up correctly. I mean, it is Friday and I'm tired, but let's just assume that I did. And we haven't actually computed these things, but let's assume that we would compute them. And actually, we can do that pretty easily in either case. Now, which version would you rather use here? The DX version or the DY version? Probably the DX version is going to be a little easier. We don't have the cube root. That's nice. We also don't have um, the y minus 1, so we won't have to worry about the chain rule or use substitutions or anything like that, right? So probably we would do it the with the dx version, but there's no reason that we couldn't do it with the dy version, and it wouldn't be that much more complicated. Okay, all right. So where are we going to go with all of this, right? So the idea here today was, yeah, you can slice things up in different ways, and you pick whichever method seems convenient for the given area that you're interested in. Okay, but where are we going to go with this sort of idea? Well, we've talked about area between curves or functions today, but what else could we do with this? Hopefully, yeah, we'll talk about solids of revolution, right? So if I take a curve and I spin it around an axis, it's going to define some sort of solid region. And maybe I'd like to find the volume of that thing, okay, or the surface area of that thing. Um, okay, so this idea of slicing it up in a good way is something that we'll use then. Other things that we could do with this would be, let's say that I have a bucket of water. Okay, so just imagine you've got a bucket of water on the table, and then 1 meter above that, I've got another bucket that's empty. Okay, and then I take like a little pump and I put a hose in the bucket that's got water in it, and another hose that runs up to the top of the bucket that doesn't have water in it. Okay, how much work does it take to pump the water from one bucket into the other? Well, okay, let's assume that it's perfectly efficient because this is calculus class, not physics. But right, point being, it's going to require me to do some work to get the water from one bucket to the other. Okay, and um, let's maybe think about it this way. Um, which is going to require more work? Moving the water at the sort of top of the bucket or moving the water at the bottom of the bucket? Hmm? Well, okay, sorry. Yeah, which bucket? Good question. Let's say the bottom bucket that's full of water. Is it going to be easier to move the water that's at the top of the bucket or the bottom of the bucket? The top is easier, okay, because it has less distance to go, right? And does I mean that just makes sense sort of realistically, right? I would hope, right? And it's going to get progressively harder the further down in the bucket you go because you have bigger distances to move that water. Well,
Water level. So you're assuming that the pump is going to the level.
yeah, so it's yeah, exactly. I mean, I think realistically you'd put the pump like the hose at the bottom, but it would almost be like imagine that the hose is like follows the water level, right? I mean, that this is sort of an unrealistic example, but um, that's something that we could figure out, and it's really going to come down to how do we slice up our bucket and how do we think of the layers of water and how much energy it's or work it's going to take, how much force. Um, to move these things, right? But we can set all of this up because calculus is in the or integral calculus is in the business of taking a thing, slicing it up, adding up the slices fundamentally, right? How you slice and how you add up is a technical detail. It's an important technical detail, but that fundamentally is what we're in the game of doing. Okay. So, good? Gucci? Oh, goodness, I ran over time. I'm sorry. Um, All right. Well, we'll quit, and I will see you guys on Monday for our next fluency assessment. Yay! And those of you who are online, I will send you guys email with instructions.